we're looking at Newton's second law. And Newton's second law kind of comes about just by a thought experiment. The thought experiment kind of says this, right? We know if an unbalanced force acts on an object, then the object is going to accelerate in the direction of that force. And that makes sense. I mean, if you were to picture, let's go down here, if you were to picture like there's an object sitting here on the table or something, and if I started to push on the object, if I apply a force to that object this way, then the object is going to move that way. If that's the only force acting on that object, or the only unbalanced force maybe acting on the object. So that kind of makes sense, right? We can also say that the greater the net force, so if this applied force here gets bigger, if that's the net force, the only unbalanced force, the bigger that force is, the greater the object's acceleration. And so what we can say is this: acceleration of an object. Acceleration is proportional to the net force. The bigger the net force, the larger acceleration the object's going to have. It's going to move faster. We can also say from inertia, from Newton's first law of inertia, the greater the mass of an object, the smaller its acceleration. And that's, again, kind of an obvious one. Believe it or not, people kind of made fun of Newton a little bit for his law, as I read at the beginning. If you picture not a very massive object, there's a small object, and then maybe over here there's a really big object. And maybe they're made of both out of the same thing, so both made out of metal or something. If you apply a force to this one, and you apply a force to this one, it's like if you're trying to push a desk or something. Let's say this one here is a desk, and over here you're trying to push a car. You kind of intuitively know the one with the bigger mass isn't going to go very fast, right? It's not going to have a very big acceleration. It's hard to get this guy going. Whereas the smaller object, like a desk in the classroom, you can push with the same force, and the desk is going to move a lot easier. It's going to have a much larger acceleration if it's a smaller mass. So you could say acceleration is inversely proportional, or it's proportional to 1 over m. If we kind of put those two thoughts together, then we get Newton's second law. And this is where Newton kind of had some brilliance. He said this. He said if a net force acts on an object, the object accelerates in the direction of that net force. He said that the acceleration is directly proportional to the net force and inversely proportional to the mass. So really, if we were to put an equation on that thing, he came up with this equation, and that was the brilliance of Newton. So if we want to go ahead and use Newton's law to solve a question to see how does this equation work, we could look at this question. Mr. Jack is pushing a large box with a force of 350 newtons to the right. Let's picture this. If we picture there's a box here. Whoops, that was the wrong thing. Here we go. Picture the box here, and let's say he's pushing with a force of 350 newtons to the right. Here's 350 newtons. It also mentions it's a 51 kilogram box. So let's go ahead and talk about gravity here. Just a reminder, gravity is mg, force of gravity. We know it's a 51 kilogram box, so we go ahead and multiply that by 9.8, and we can say Fg is 499.8 newtons. If that's Fg, Fn, same thing, 499.8 newtons, because this force is equal to that force. And then we've also got some friction going back this way. And let's just keep in mind, friction is mu times the normal force. So I'll go down here and do it. Friction, mu Fn. Let's see, we know what mu is. Coefficient of kinetic friction is 0.4. So 0.4. Normal force, 499.8. It's an 8. And we get friction, let's see, 199.92 newtons. There's friction. We're asked to find the acceleration of the box. So in this question, we're going to have to use Newton's law, and I should say this now. I always seem to forget this in my questions. So let's go ahead and say, let's make this forwards direction. That's going to be our positive direction. For up and down, doesn't really matter, but when I go ahead and use Newton's law, it says the sum of F equals ma. Okay, so this sum of F, just like we've talked about before with the sum of displacements, sum of F means add all the forces together. So when I add the forces together, it's going to be all the unbalanced forces. Normal force and gravity, those guys cancel. So I don't need to worry about them. I just need to worry about applied force and force of friction. So applied force plus force of friction. Now do notice that force of friction is in the negative direction. So I'm going to go ahead and stick my negative sign on right here, just to show you it's in the opposite direction. Sometimes people don't like to put the minus sign there. They don't like to put the minus sign in until we get until we start subbing numbers in. But I'm going to go ahead and put it in now. So the applied force, we know that one, 350 newtons, plus negative force of friction, so 199.92, and that's equal to the mass of the box, 51 times A, and it's A that we don't know. So we can go ahead and subtract this, and we'll get 150.08 equals 51A. We can divide both sides by 51, and we get acceleration 5.88 meters per second squared. And let's go ahead and do some good sig digs here. 5.9 meters per second squared, and that is to the right, according to my diagram, and I guess according to the question too. And there it is. This next question is a little easier, well, maybe easier, but a little different anyways. Here we're looking for what applied force is needed in order to give it 5 meters per second squared. I don't know why my units always mess up when I do this. This is per second squared. Okay, so meters per second squared forward. Let's go ahead again and we'll draw our free body diagram. So here's an object. We know we're applying some force. We don't know which way, but let's say forwards. This is something I don't know, so I don't know what this applied force is this time. Force of gravity, though, that'll be down. Normal force up. This book is resting on some surface. And as is usually the case, as long as we're on level surfaces anyways, normal force and gravity, they can cancel. Force of friction, back this way. That's friction. We're given friction this time. It's 8 newtons, 8.0 newtons. And we're also given mass, as is typical. Remember, Fg is mg. So let's see, this is 3 kilograms times 9.8. And that force of gravity is 29.4. That's 29.4 newtons. So is the normal force. We actually didn't need to calculate either of those this time, so there's a little extra work for nothing. But it's good times, good practice. Because we were given friction as a number, we were told friction was 8 newtons, rather than giving us the mu value. This question actually gives us the full value for friction, so I didn't need to calculate those, but let's face it, this is a lot of fun, so always good times to calculate a few extra things. We can go ahead and use Newton's second law now, and just like we did last question, I'll stick with this direction being our positive direction, our forwards direction. And just like last time, we've got applied force minus force of friction, or you could say plus negative force of friction equals ma. Remember, friction is negative because it's in the negative direction. That's why that number went in as a negative, or that value is going to go in as a negative. Friction is 8 newtons. The mass of this object is 3. And here in this question, we're told that acceleration is 5. Right up here, 5 meters per second squared in that forwards direction. So we can go ahead and calculate 3 times 5 we know is 15. And I'm going to bring this -8 over to this side. So it's going to become +8 on that side. And I'm still left with applied force here. And so this applied force ends up being 23 newtons. And that's in our positive direction, forwards. I need to push with a force of 23 newtons forwards in order to make this object accelerate at 5 meters per second squared.